Okay, let's come back to this odd looking definition for the dot product. So that v dot w is length of v times the length of w times the cosine of the angle between them. There isn't much in the way of a geometric interpretation of this expression, but if you think for a moment, if this were a sine theta instead of a cosine theta, then that would give you the area of this triangle. Okay, but we don't have a sine theta, we have a cosine theta. Okay, so if you consider though just part of this expression, let's take the length of w times cosine theta. No, let's instead rewrite this. We should say that v dotted with w is the same as w dotted with v, because in that case it would be the length of w times the length of v cosine theta, which is the exact same expression. Okay, so it's commutative, the dot product. I should also say that when you work out the dot product, the answer is a scalar, some scalar. Okay, so the answer is some scalar k. Okay, good. So what I'd like to do though is, if we examine part of this definition, okay, so if we examine, let's take this part here, length of v times cosine theta. Well, if you look at this triangle here, this right angle triangle, there's your angle theta. The cosine of theta is this side of the triangle here. So if we give this red vector a name, let's call it u, the vector u. The cosine of this angle theta is the length of u, which is the adjacent side, divided by the hypotenuse, which is the length of v. Okay, which means that the length of u is the length of v cosine theta. So this part of the expression here is the projected length of the vector v onto w, okay, which is the exact same as if you had projected w onto v. Okay, so you can think about the that part, that separate part of a dot product as a kind of a projection. Okay. Right. So there are three things that we can, three expressions that we can derive, three quantities that are relevant in all of this, that we can write in terms of a dot product. The first is length. Okay. So we can find the length of the vector v. Okay, the length of the vector v that is equal to v dotted with itself. Okay, if you dot v with itself, you get length of v squared times the cosine of the angle between it is 1, so that's length of v squared. So actually this is the length of v squared. Okay, so that means that the length of the angle v is equal to the square root of v dotted with v. Okay. The other thing, the other quantity that we can find is the angle, theta. So we know that cosine theta is the same thing as v dotted with w divided by the length of v times the length of w. Okay, which is the same thing as v dotted with w divided by the square root of v dotted with v times the square root of w dotted with w. So everything there is written in terms of dot product. Okay, which we can compute perhaps using the coefficients or the components rather of the vector in some basis. The last thing we can do is think about the projection. So the projection is the vector u, we called it. So if we go back up here, this is the vector u. We want to, instead of finding the length along here, we want to find the actual vector u itself, the vector which has direction. Remember that the dot product gives us a scalar, not a vector, as the output. So if we want to find a vector, we have to do something slightly different. We begin along the same lines, so we can say that the vector u is going to be the length of u, which we figured out was the length of v times cosine theta that's the length of u. The length of u was length of v cosine theta. Okay, that's just the length, the magnitude of the vector u. But to get its actual, the expression for the actual vector u, in that case we have to find a unit vector in the direction of w. And you can find a unit vector in the direction of w by multiplying this by w divided by the length of w. That will give you a unit vector in the direction of w. So that is our projection u. But it's unfortunately, as it is at the minute, it's not written in terms of the dot product. So let's change this to the length of v is the same thing as v dotted with v square root times the cosine of theta times w over the root of w dotted with w. Okay, we're still not exactly there yet. So what I'm going to do is multiply above and below by w dotted with w. W dotted with w, which allows me to combine these things. So I will take this length of v and this length of w and the cosine theta, and that allows me to write that that's the same thing as v dotted with w divided by these two multiplied by each other just gives me w dotted with w times w itself. So this is the vector u. which is a kind of projection of the vector v onto the vector w. So all of these are written in terms of the dot product, and we've kind of examined a little bit about what the dot product, or where the dot product can get us. Okay, and as I said before, even though we've defined the length here in terms of the dot product of two geometric vectors, using the idea of inner product, which is an extension to more abstract spaces, we can even find the length of a polynomial. So this is really quite useful. Okay, in the next video we're going to move on to orthogonal transformations, orthogonal matrices.